Okay, here we go now. Moving along, trying to extend the ideas of section 6.1, which is all about finding the area under a curve. So here's what we'll do. We'll just consider any continuous function at all. And let's look at it from, say, A to B. And what we're looking to do is to find the area under that curve. And what we'll do is we'll consider n rectangles, and each of them will have a equal base, and so we'll call the base delta x, and its length will be b minus a divided by n. And let's assume that we're going to be using LRAM, using the left-hand endpoints. So basically, if we just think about breaking this up into a bunch of subintervals or a partition, and we use the left-hand rectangles, well, we get something that looks like this. Whoop, we're down below again, one more time, now we're up, and there we go. So we see that some of these rectangles are above the x-axis, and some of them are below. And we have to understand what the question is being asked at all times. If it's area, then what we've got to do is make each of these expressions be positive. Now, think about it. When you find each of these rectangles, it's going to be f of x times delta x. Well, as long as the rectangle is above the x-axis, that product will be positive. When f of x gives you a negative value, as it does in these, then that product will be negative. And in order to talk about the area under a curve, we've got to make any of these so-called negative areas be positive. Okay, so what does LRAM equal in this case? Hopefully we'll have enough room to write it out. So LRAM is equal to, the common base is delta x, I'll take that out. And what I have then is going to be f of a plus f of a plus delta x plus f of a plus 2 delta x, and we continue like that until we get to, I'll write it down below, f of a plus n minus 1 times delta x. And that is LRAM. And if I can just squeeze it in, I'll introduce you to sigma notation. And this is exactly the same as the sum as k goes from 0 to n minus 1 of f of a plus k times delta x times delta x. So this is the first time we're seeing this notation, this so-called sigma notation. And all it means is start off letting k be 0 and add up all of these expressions until k finally gets to n minus 1 and then stop. So 0, 1, 2, and you keep going, you stop when you get to n minus 1. It's just mathematical shorthand. Okay, let's keep pressing ahead. So what we want to talk about is how do we find the exact area? LRAM, RRAM, MRAM all give us a pretty good approximation. And if we let n get larger and larger, the approximation gets better and better. So let's talk about what's known as a Riemann sum, which is as general as we can make this idea of adding up the rectangles. And so we do this. We break up the interval, let's say from A to B, into n pieces. And we let C sub k be any x in the kth subinterval. So then what we have is what's called a Riemann sum, and it's not really an LRAM or an RRAM. All it is the sum as k goes from 1 to n of f of c sub k, in other words, just any height at all, not the left, not the right necessarily, not the middle, just any of those heights, times delta x. And that gives us an approximation for the area. Well, let's call I the exact area. Now, I think you see where this is going. And the exact area is equal to this same expression as k goes from 1 to n of f of c sub k times delta x. But what we do now is what we've been talking about all along. We take the limit as n approaches infinity. And that's really the same as the limit as delta x approaches 0. And this is the big idea. This is what gives us an exact area under a curve. And it's all about our old friends, the limit. So just as the limit was central to the idea of finding a derivative, the idea of a limit is central to the idea of finding an area under a curve, which we'll soon see is equivalent to finding the integral of a function. So we tie together this idea within a very important definition. And what we say is that if I is equal to this limit, and if that limit does indeed exist, then we say that f is integrable over the interval ab, and I is the definite integral of f over ab. We have an important theorem here that tells us when a function will be integrable, and it simply says that as long as a function is continuous, it will be integrable. And understand that all that has to happen is continuous. The function does not have to be differentiable, just continuous. So it's helpful here to introduce some notation. Mathematicians are notoriously lazy. They're always looking for easier ways to write things. And this limit that we've looked at for a long time, which gives us the exact area, we write in a much simpler way as this. And we read it as the integral from a to b of f of x dx. And it simply is a shorthand way of expressing this much longer expression. And just again to try to drive a point home, this piece is a Riemann sum. When I consider the limit as n goes to infinity, I get the exact area. Alrighty, so what we'll do now is look at a rather challenging example that'll show you how we can use these definitions and this notation to find the exact area under a curve. So in this case, we're looking for the exact area under the curve from 1 to 3 of y equals x squared. And that's exactly what this notation tells you to do. So when we found the derivative using the definition and found it to be pretty clumsy, the only method that we have right now is similar, and we will learn in 2 sections, I think in section 6.4, a much easier way of doing it. So here we're going to break this interval from 1 to 3 into n pieces and let n go to infinity. And so what that implies is that each delta x is 2 over n. So I'm going to factor out 2 over n from each of these heights. And I'm using right rectangles, so my first height is 1 plus 2 over n squared plus 1 plus 4 over n squared, oh, what messy, plus 1 plus 6 over n squared, and I keep going until I get to 1 plus 2n over n squared, which is the same as 3, but I want to write it in the same form. Okay, so I'm going to put in some steps here while you're reading so that it doesn't take that long, and hopefully you can follow along. So what I've done is simply performed all of these squares. So that's what that is, that's what that is, that's what that is, and that's what that is. So that's the first step in this algebraic process. And here I've basically taken all of these 1's and written them as n times 1 because there's n of them. Then out of these middle terms, I have factored out 4 over n, and I get 1 plus 2 all the way up to n. And out of these third terms, I've factored out 4 over n squared, and I get a 1 plus 4 plus 9 up to n squared. So notice that this is the sum of the first n integers, and this is the sum of the squares of the first n integers. So we'll finish this up on the next page. So in order to complete or simplify that previous expression, we need to make use of two very important formulas that have to do with the natural numbers. First one is that the sum of the first n integers is n times n plus 1 over 2. And the second one, the sum of the squares of the first n integers is n times n plus 1 times 2n plus 1 over 6. So these are two statements that can be proved by mathematical induction. And so here in red, I make those two substitutions, and we continue simplifying. So we do a fair amount of simplifying here, and we come down to this expression. Now, one of the things to notice is that this is a rational function, and this is a rational function. And you remember about limits as x or as n goes to infinity. Degree is 1 on top and bottom. The degree is n cubed on top and bottom. So this piece will just go to 4, and this piece goes to 16 over 6. And what that means is that this limit is equal to 2 plus 4 plus 16 over 6, which simplifies to 26 over 3. And there is our final answer for the area under y equals x squared from 1 to 3. Now, wasn't that fun? Clearly, there must be an easier way to compute this area. Just as with derivatives, there was an easier way to compute it rather than using the definition. And as I've said a few times, we will look at that pretty shortly. It's probably worth mentioning at this point that these integrals can also be done on your graphing calculator. That's a technique that we'll examine in class, but I'll remind you that both manuals for either the TI-89 or the Inspire are found on the math webpage at nmhschool.org. So that'll help you remember how to do it if you need to.